Okay, so we're going to improve the inscribed quadrilateral theorem, which states that a quadrilateral is cyclic, aka can be inscribed in a circle, if and only if the sum of each pair of opposite angles is 180. So since this is an if and only if statement, we're going to do the P implies Q first. So that means we're going to let A, B, C, D be cyclic, right? So let A, B, C, D be cyclic. So remember, that just means that A, B, C, D can be inscribed in a circle. So since it is inscribed in a circle by the inscribed angle theorem, we know that the measure of angle BAD, or angle A, is equal to half its corresponding arc, which would be arc BCD, right? So the measure of arc BCD and the measure of angle C is equal to half the measure of its corresponding arc, which is BAD. Right? So hopefully you guys can see that arc BCD plus arc BAD is 360, right? So we know the measure of arc BCD plus the measure of arc BAD is equal to 360. And I'm going to try to get these 1/2s, right? So I'm going to multiply both sides by a half to get 1/2 the measure of BCD plus the measure of BAD, right, would be equal to 180 if I multiply a half on both sides of this equation, right? And of course, gives us 1/2 the measure of BCD plus 1/2 the measure of BAD is equal to 180, and BCD plus BAD is just the measure of angle A plus the measure of angle C is equal to 180. And you can use a similar argument to show that angle B and angle D, their sum is 180, their sum is 180. So by the inscribed angle theorem, we know the measure of angle B is equal to half of ADC, and measure of angle D is equal to half the measure of ABC. All right, we know that ADC plus ABC is 360. So the measure of ADC plus the measure of ABC is equal to 360. If I multiply both sides by half, I get, let me scoot this a little bit. Okay, I get 1/2 measure of ADC plus 1/2 measure of ABC is equal to 180, which of course means that the measure of angle B plus the measure of angle D is equal to 180. So we've proven that if ABCD is cyclic, then the sum of the opposite angles is 180, right? So this is an if and only if statement. So now we're going to move on to the converse. So the converse says, right, if we have quadrilateral ABCD and the sum of the opposite angles is 180, then that quadrilateral must be cyclic, right? Okay, so we're going to prove this by contradiction. So of course this is the Q implies P. So we will be proving by contradiction using the equivalence. So remember, the negation of Q implies P is equivalent to Q and not P, right? So if we can show that Q and not P is false, that means that the negation of Q implies P is false, which means Q implies P must be true. So remember, Q was if we have a quadrilateral ABCD, and we have the opposite angles, the sum of the opposite angles is 180, right? So that's Q. We have ABCD. We're going to assume that ABCD is a quadrilateral where the opposite angles, the sum of the opposite angles is 180, and then P is, then ABCD must be cyclic, right? So if we're going to do this by proof by contradiction, we're going to let ABCD be a quadrilateral where, of course, the measures of the opposite the sum of the opposite angles is 180. So BAD plus BCD is equal to 180, and ABC plus ADC is equal to 180. And so that's Q, and we're going to assume the negation of P, which is ABCD is not cyclic. So now, since A, B, and C are non-collinear, there exists a unique circle T that goes through points A, B, and C. So notice I have this circle, and it goes about points A, B, and C. So there are infinitely points on any circle, right? So we're going to let D prime be an element on circle T, making ABCD prime cyclic, right? So if ABCD is not cyclic and ABCD prime is cyclic, this means that D and D prime are different points. And of course, by the first thing we proved, P implies Q, we know the measure of angle BAD prime plus the measure of angle BCD prime is equal to 180, and the measure of angle ABC plus the measure of angle AD prime C is equal to 180. Okay, so if we draw the circle about points ABC and we include this D prime, we know D prime can be in only two possible locations. We know that it can be in the interior of ABCD, which is this picture here, right? And we know that D prime can be located in the exterior of ABCD, right? So what we're going to do is we're going to show that there's a contradiction for when D prime is in the interior of ABCD and when it's in the exterior of ABCD, leading to that it must be the case that ABCD must be a cyclic, right? So the first case is D prime is in the interior of ABCD. So this implies that the measure of angle BAD is bigger than the measure of angle BAD prime, right? So BAD is going to be bigger than BAD prime, right? Since D is in the interior, we can clearly see that this angle BAD is going to be bigger than this angle BAD prime. Similarly, we have, and the measure of angle BCD is going to be bigger than the measure of angle BCD prime, right? We have BCD is going to be bigger than BCD prime. Okay? So, of course, this implies that the measure of angle BAD plus the measure of angle BCD is going to be bigger than the measure of angle BAD prime plus the measure of angle BCD prime. Now, remember, we assumed that ABCD prime was cyclic, which by the first thing we proved, that means that the sum of the opposite angles is 180. So this implies that the measure of angle BAD plus the measure of angle BCD is bigger than 180. But remember, we also assumed that for quadrilateral ABCD, that the sum of the opposite angles are 180 in that, right? But we know that the measure of angle BAD plus the measure of angle BCD is equal to 180. Well, we know that both these statements can't be true at the same time, so this is our contradiction, right? So it can't be the case that D prime is in the interior of ABCD, where for ABCD, the sum of the opposite angles is 180. It can't be that case. So let's go ahead and check the case when D prime is in the exterior of ABCD, right? So we can see this implies that the measure of angle BAD prime is bigger than the measure of angle BAD, right? We can see that BAD prime is going to be bigger than the measure of angle BAD. And of course, the measure of angle BCD prime is going to be bigger than the measure of angle BCD, right? BCD prime is going to be bigger than the measure of angle BCD. So this implies that the measure of angle BAD prime plus the measure of angle BCD prime is going to be bigger than the measure of angle BAD plus the measure of angle BCD. But remember, we assumed that quadrilateral ABCD was in a way such that the sum of the opposite angles of that quadrilateral are 180. So this implies that the measure of angle BAD prime plus the measure of angle BCD prime is bigger than 180. But remember, if ABCD prime is cyclic, that means the sum of the opposite angles of ABCD prime are 180. They're not bigger than 180, right? But the measure of angle BAD prime plus the measure of angle BCD prime is equal to 180. Of course, we can't have both exist at the same time, so this is a contradiction. So in both cases, when D prime was in the exterior of ABCD and when it was in the interior of ABCD, it led to a contradiction. So that means D and D prime cannot be different points, right? D must be a point that lies on ABC, right? On this circle T that's a circle containing ABC, right? So thus, in both cases, Q and not P is false. This implies that the negation of Q implies P is false, which means the original statement Q implies P is true. Therefore, for quadrilateral ABCD, if the sum of each pair of opposite angles is 180, then ABCD must be cyclic.